Hello everyone. So today me and Vikram are going to talk about TensorFlow optimizations on modern Intel architectures. We are representing the work of several Intel teams over the last couple of years. So this slide just gives you a brief overview of what we are going to spend most of our time today. So I will begin my talk by setting some context as to why Intel is interested in TensorFlow and what is the motivation behind this work, and briefly give a high-level overview of TensorFlow optimizations that the Intel engineering teams have done, and show some performance results on both multi-node and single node. And then switch gears a bit and then give a kind of like a high level usage of how users can use TensorFlow in terms of installation, and then how do they set the right runtime settings, and how do they profile, and some potential issues that one may encounter, and then finally close out by showcasing some benchmarks and case studies that we have done on mostly Skylake and Ice Landing. So as people may know already, that TensorFlow is a popular open source machine learning and deep learning framework. Mostly, I think it was originally developed at Google and then open sourced it back in 2015. So it's widely used in the industry for several applications such as image classification and speech translation and text recognition stuff. It is mostly written in C++ as in the backend, but most of the data scientists interact with it in the form of the Python front end. It has several other language support, but Python is the most widely used front end for TensorFlow. And it also has good multi-node support, so we can run the framework itself can be run on multiple nodes of CPUs or GPUs. In the last year or so, it has gained popularity among the scientific community as well. In some cases, we have seen the high energy physics scientists and some climate scientists have used the TensorFlow in applying some of the machine learning techniques in doing some scientific breakthroughs. I just want to here highlight like the two of our latest Intel architectures in the form of Skylake and Night Landing. Those are the code names, but the official names are the Intel Xeon and Xeon Phi platforms. So they deliver significant performance gains compared to the previous generation of Intel processors in the form of AVX512, which is the new instruction set that is introduced in these processors. So for people who are not really familiar with AVX and AVX512, I just put a small table on the right to give you a comparison. So AVX2 was the previous generation of Intel processor, which basically stands for Advanced Vector Extension, where the register length was 256 bits. And with AVX512, we doubled the register width as well as the number of registers available on the processor itself. So the register width is now 512 bits, and the number of FMAs you can do remains the same, but since the vector register is doubled, so you can do more flops per cycle. So essentially you can do 64 floating point ops per cycle for single precision, and for double precision you can do 32. I just want to point out that all the machine learning work, or all the work that I am showing here, is using single precision, which is a difference between HPC and deep learning. So you will see some of the pattern. There are some similarities and some differences between HPC domain applications and deep learning applications. And one such difference is the precision that is being used in the workload. So both Skylake and Night Landing has AVX512, and they have on Night Landing, as you may know, I think Argonne already has a KNL machine on site. So KNL has this high bandwidth MCD-RAM memory, which delivers significantly better memory bandwidth than DDR. So the motivation for Intel is basically, as a CPU vendor, we are interested in understanding the emerging software stack or software, what are the latest emerging software frameworks that are being used by our users or scientific community, at large sets like Argon, and basically optimize these frameworks to extract maximum performance out of the platform. And these typically involve vectorization to maximize FMA unit utilization, and some of the standard HPC optimization techniques that also apply in deep learning. So these involve some cache blocking algorithms and parallelization to make sure you have ideal load balancing among all the cores. So I just wanted to kind of give a very high level stack overview of what TensorFlow looks like from a runtime view. So if you see on the left side, you have your TensorFlow baseline, which basically the dotted line differentiates the front end to the back end. So if you are a user of TensorFlow, you typically don't tinker with anything on the back end. You only interact with the front end. But if you are actually like a developer of TensorFlow itself, like me or some other people at Intel, we mostly focus on the back end, and we don't want to change the front end of the framework pack. So basically, in the baseline case, you will see that the data scientists use the Python front end to write up their machine learning application, which then gets converted into a data flow graph by the TensorFlow framework, which is basically driven all in the C++ runtime. So the data flow graph is basically a set of nodes and edges where the edges represent data flowing from one computation to the other, where the nodes are the actual operators of the computation operations of the network. And then these operations on the baseline case go to Eigen, which is a open source C++ template library for doing these convolutions, matrix multiplications, and such activation functions. So on the optimized case, we made a very conscious decision not to tinker anything on the front end, because we don't want the users to change anything in their models, and we only focused exclusively on the back end, wherein we tuned the data flow graph, and we also added Intel MKL APIs into the framework itself. So I'm going to talk about these graph optimizations and MKL DNN in the next slide. So as people in HPC community may already be familiar, MKL is a widely used in math library for acceleration of numerical linear algebra functions for the last good part of 15-20 years. So we kind of extended that library to also have specific APIs targeted for optimization of the deep neural network functions that are used in most of the machine learning applications. So this library has specialized almost assembly-like kernels for the DNN primitives. I have listed some of the primitives here and classified them into different classes of like whether it is compute intensive or memory intensive. So basically, we do have good coverage of all the ops that are widely used in several convolution neural networks or some speech translation models. And we have dedicated kernels based on the ISA. So if you are using a KNL, you have a dedicated kernel that is optimized for KNL, and if you have a Skylake, you have those equivalent stuff for Skylake. And the library itself uses multi-threading based on OpenMP. And one significant change we have is we have fully open sourced this library. It's all available on GitHub. So if people can see what are the APIs look like, what are the optimizations that we have done, and things like that. So the major difference is the Eigen implementation of DNN primitives for Intel hardware is not optimal, and there is significant performance gains that can be realized by tuning it. And we have used it. We typically use MKL DNN to get this performance gains.
So we have a question. Does MKL DNN do the same function as NVIDIA's CU DNN?
Yes, it does. Yeah, they are not API compatible, but they do the similar computation, similar work. Just like how they have cuBLAST, we have MKL BLAST. cuFFT, we have MKL FFT. Similar in the similar fashion, yes, but that's true for DNN also. So in this slide, I'm going to talk about the graph optimizations that we have done to the backend. So as I was mentioning, TensorFlow does a data flow graph where you have, for example, in the picture I'm showing, we have a convolution function wherein we have the inputs and the filters followed by a activation in the form of a ReLU. So here what we do is convolution is a compute bound operation, whereas ReLU is basically a memory bound. And we have found that this pattern of memory bound operations are, we do end up spending significant amount of time in these memory bound ops. So what we do is we try to minimize the amount of pressure on the memory channels, and then we fuse these two kernels into one, where we have equivalent conv 2D plus ReLU in MKL. So we kind of use that to do this computation. And one more key optimization that we do to the backend is in the form of memory layout optimization. So if people have used image CNNs for image classification, they would know that the most common memory layout for doing these kind of computations is in the form of NHWC or NCHW, which basically at a very high level stands for H is your number of pixels in the horizontal dimension, width the width is the number of pixels in the vertical, and the C is the number of channels you have, and N is the number of images that you are processing in that batch. So while we are doing this, while these are natively supported by the TensorFlow framework, Intel MKL prefers a more blocked layout of these tensors, which we, for example, for Skylake or for Kernel, we prefer a blocked layout in the form of where we are blocking by a number of 16 in the channel dimension. So for this block transformation, what we do is, so we have to convert from TensorFlow format to MKL format whenever we are calling MKL primitive in the graph. So if you see in the initial graph, this is what happens in the baseline case. And in the second graph, you see we have changed these APIs into MKL counterparts. And when we change them, we need to transform the tensor as well into this data format of blocked data format that we have in MKL. So as you can observe that we don't want to do it over redundantly, because if there is a MKL op, for example, in this case, you see a conv 2D. After a conv 2D is completed, we are converting MKL format to TensorFlow format. And again, in the ReLU op, we are doing the opposite, which is redundant, right? So what we typically do is we find the largest subgraph in the where we have a continuous flow of MKL ops, and then we essentially remove these conversion nodes and directly minimize the amount of time spent in the memory layout transformation routine. So that framework itself tracks this and only does this when needed. So the users don't have to really worry about this. And in addition to the graph optimizations I mentioned, we also have implemented a memory pool or a memory manager for all the neural network operators, which they allocate significant chunk of memory. So the default memory management routines in TensorFlow they don't really have their own pool allocator. So whenever you are doing a memory allocation or a deallocation, it is essentially you pay a significant cost of overhead of these functions. So instead, what we do is we allocate a chunk of memory when the first allocation request is made, and then we keep on reusing those pool until the next allocation routines as well, where possible. But of course, there's upper limit on how much we can do on this. But we have found that this has improved significantly for some of the benchmarks that we have used. So at this point, I just want to I gave a brief overview of what are the optimizations that we have done for single node. So I just want to show what are the gains performance gains that you can observe by comparing Intel TensorFlow versus the baseline that you get. So on the left you have the Knight's Landing, and on the right you have a Skylake. Both of them have AVX quite well. So the x-axis represents basically a set of standard benchmarks that are used in These are essentially equivalent of your LinPack or your GEM benchmarks in HPC domain. So here you have, as you can see on KNL, if you use Intel version of TensorFlow, you can get a significant speed up ranging anywhere from 20 to 40x. Similarly, on Skylake, you can get anywhere from 8x to 14x compared to baseline. So the configuration details, and one thing I want to note is that on the night landing, we tested with a slightly older version of TensorFlow compared to the Skylake one. So there is some, so this is not exactly the same version of TensorFlow is being used, but essentially, but the baseline version is it's a fair comparison compared to the baseline. So in addition to the single node optimizations, TensorFlow, as I was mentioning, also has support for distributed parallelism in the form of several. There are two main mechanisms of doing distributed computing with TensorFlow.
Excuse me for just 1 second. We had a request to clarify baseline. I believe you're talking about the non-MKL
Yes.
Tack, right?
That's right. So if you, when I say baseline, I mean this chart on the left, which basically is not using MKL. It doesn't have any of the operator fusion, memory layout transformation, or the memory manager optimization involved in it. So distributed TensorFlow. So basically, if you want to run your convolution neural network model on multiple nodes, it's basically a data parallelism mode wherein you run the same model on different nodes with different data. So basically, essentially, it is a strong scaling problem, and where you have there's no load imbalance because every worker is doing the same amount of computation with different data. And then we have like two different mechanisms of doing it in TensorFlow. One is the native mode is the Google RPC procedure, which is basically a typical master worker model. As you can see in the picture on the right, this requires a set of workers are assigned to a parameter server, which is where the gradients of the weights are aggregated and then distributed back to the workers. So you can imagine the parameter server is not essentially doing any kind of computation. It is only coordinating the like the weights from all the workers. And as you can imagine, this has a significant scaling bottleneck when you go at scale, where you have a large number of workers all using the same parameter server, or you need to dedicate a certain number of parameter server to a certain number of worker nodes. And then, but there is a much more efficient way of doing it, which uses MPI, which is widely used in HPC domain for several years now. So that is originally developed by Uber. They developed a TensorFlow Python plugin in the form named as Horoward. So it kind of uses MPI, and they kind of overlap the communication with computation while they are doing the backward pass, so that you don't do the reduction, you don't do the all reduce all at once, rather than in layer wise fashion. And then Intel also has a machine learning scaling library which does better performance than Horoward, wherein we have tuned MPI all reduce for the sizes or for the communication patterns that are usually encountered in DNN models. So you can look at I put some link on the right side, so you can easily check out some of these links and try it out. So this slide kind of shows you what is the scaling, how does the scaling efficiency you get by comparing Intel MLSL and Horoward on Intel Skylake nodes. So we have a much more bigger scaling results in the next slide, but I just wanted to kind of capture the improvements MLSL delivers over Uber's Horoward, which is basically an MPI plugin. So as you can see, like at 60 nodes, we kind of have a very, very good scaling efficiency of about 95% for both the ResNet and Inception V3, which are two standard DNN topologies that are used for image classification. So at this point, I want to switch gears a bit and kind of give an overview of how people who are interested in trying TensorFlow on Intel architecture can use it. So basically, all our optimizations to TensorFlow are upstreamed regularly. So we haven't forked TensorFlow or done anything like that. It all goes to the master branch of TensorFlow. So one can we provide pre-compiled binaries for as TensorFlow releases, we release the same version that uses MKLDNN. So for example, you can install these through pip, depending upon which version of Python you prefer. You can get either from the links we have in the slide. So if you want to, for example, try the greatest version of TensorFlow with MKL, then you can definitely clone the Git repository, do a configure, and the Bazel is the build tool that is used by TensorFlow to compile. So here, if you see, you just have to specify config equal to MKL, which basically downloads the MKL library and then configures TensorFlow to use it. So you don't have to tinker any build files or anything like that. And then you get the wheel file, and then you just install it and start up the Python runtime. So I wanted to focus on the runtime settings of TensorFlow because these.
Excuse me. Venkat, did you have anything to add about what we have pre-installed?
Yeah, so we have, I believe TensorFlow 1.6 as well as 1.4 installed on our systems, and we are also working on getting 1.8 and 1.9 installed at our end. And so, so in the build tool, when you're building this, in this current, you have a config file that says config that pulls in MKL. So two things that we have on our system is the need to do. So if you want to specify a version of MKL DNN, it would be good to know from you what would one need to do that. I'm guessing it's just setting up a flag. And what kind of compilers would you recommend? For example, GCC versus ICC, and your thoughts on it. And finally, there's a thing of cross compilation, but we can come to that next.
Mm-hmm. So in terms, I didn't quite understand the question about the version. So when you just give this option, right, it will TensorFlow already has a which version of MKL is to be downloaded is already pre-configured with TensorFlow. So whenever there's a new release of MKL available, this TensorFlow is updated to basically check out that version of MKL when you are building the latest master. Okay. So you don't have to really, yeah.
So in this case, if you want MKL DNN as well.
Yes.
When he meant MKL, he meant MKL DNN.
Yeah, exactly. When I say MKL, we actually meant MKL
DNN.
Okay. And so, if we want to specify some specific MKL and MKL DNN versions that we have.
It is kind of, I believe there are some environment variables that you can set when you are building the TensorFlow itself, which will be read by the build system, and then it will pick up that version of MKL that you have on your local disk, basically. If you don't want it to be checked out from, because that requires a network connection to an outside world and things like that. But I'm not exactly that. I need to check actually. But we have used it internally on and off. I don't know how well, but the recommended way for our users is just let TensorFlow figure out which version of MKL and MKL DNN is being pulled in into the build process.
And what compilers would you recommend in this case?
So we recommend standard GCC compiler. But we do, however, recommend a higher version of GCC which can generate efficient AVX512 instructions. The reason is the two factors. There is a two-part reasoning for this. While the compiler has no impact on MKL, so since most of the topologies use MKL heavily, which version of compiler you use or what flags you use into the compilation has a minimal impact for all those MKL functions because it's a pre-compiled library already. So but it does have some impact for non-MKL operations in TensorFlow. So if your topology has significant amount of non-MKL operations, then the performance dependent upon which compiler or which version of compiler you use. So we typically recommend GCC with anything greater than, I believe, 5 or 6.2. Yeah. Which basically can recognize AVX or can generate AVX512 at least. That's the recommendation.
Okay.
And is there any other question?
No, I think those are the two.
Those are the two. Okay. So if I can go to the next slide, right? So the runtime settings. So the runtime settings, these are can be significant part of the settings are related to threading, which I have listed these different parameters here. So basically you have your inter-op parallelism threads and your intra-op parallelism threads. These are two parameters used by the TensorFlow framework itself. So you can view the inter-op as a graph level parallelism. So let's say you have a graph where you have two independent subgraphs and you can execute these two subgraphs in parallel. So in that case, you want to specify your inter-op parallelism threads to 2. So that basically says like, hey, I want to use two main threads to start executing simultaneously. And intra-op parallelism threads basically tells you how many threads you want to use for any of an operator in the graph. So at a high level, for HPC people, this kind of like is equivalent to your inter-op is equal to your MPI, where your intra-op is kind of equal to your OpenMP. So if you are think of it as like a hybrid parallelism in that way, and then you need to set OMP num threads as well, because Intel MKL uses OpenMP and it does not actually read any of the inter or intra-op. So it has no view of how many parallel threads are running at the framework level. So when you set OMP num threads, you need to make sure that you set it to, so basically don't oversubscribe it and set it to the number of physical cores you have to a TensorFlow instance. And the KMP affinity and the KMP block time are basically the two environment variables that are read by the Intel OpenMP runtime library. So the affinity makes sure that you don't have any threads are not moving during runtime, and we are basically pinning them to the physical cores available on the chip and not the hyper-threaded cores. And the block time basically this is a number, the default value is 200, which is too high. This basically is a time in milliseconds that a thread after completion of its work, how quickly does it go to the sleep state, so that the next time a parallel section is opened, those resources are freed up. So we have seen cases where it's typically set from 1 or 30. So these are some things. The block time is something that there is no one setting that is good for all topologies, but it varies from some. We have seen cases where a setting of 1 is significantly better than the default. And we have a link here that kind of we have provided these recommendations directly documented on the TensorFlow webpage itself for future reference. When you are trying these models, you may want to read these and set these parameters accordingly. So in terms of memory, the only thing is, I think you guys may already know this. So since Kernel has MCD RAM, you obviously want to use it where possible. If it's in flat mode and your app memory is less than 16 GB, we definitely recommend to use it in flat mode. If not, then if it is in cache mode, then you don't have to do anything special. It will MCD RAM will automatically work as a level 3 cache. So one other thing that we observed is when doing TensorFlow on large core count machines or on chips, like a single worker instance may not fully optimize the CPU runtime. So we want to basically use multiple CPU work or TensorFlow workers on a single KNL die. So here in this example that we are showing, we have basically 4 workers. So the KNL die is partitioned into 4 domains, and you pin the worker to those cores, and you set your affinity with explicitly pinning to those cores, and set your OMP num threads accordingly, and then you get and you can get better performance through efficient utilization of your cores. And so basically this is something that you can try without any modifications in your model in your models basically. Just, and we have written several blogs on this, so we provided the links. So all the runtime settings, so the benchmarks, how they can be executed, we have documented it there, because it's too much of a content to put in one slide. So we just wanted to point those out to you. So next part is from a usage point of view, right? Let's say you already have a model and you have installed, you have tried this, and you want to see, hey, what is my hotspot, or how is the performance of the model doing? So here we have, like, TensorFlow itself has a native profiling APIs. They are called as timeline APIs. So as you can, so these APIs typically you need to put it in your Python code, which basically I put a link here. This kind of shows you a very like an intro of how you can simply put those API into your graph. So basically it's a hook to your graph, and you don't have to do any heavy lifting of putting a timers or anything like that. So once you put those API, TensorFlow will dump a JSON file consisting of all the operators and the time taken in each of the operators. And then you need to load this JSON file into a Chrome browser, and this is the picture that you will see once you load that JSON file. So this is, as you can see a list of the the most time-consuming functions in this particular model. This I have used a ResNet running on with MKL optimizations to TensorFlow. So you can see like all the time is spent in MKL functions, which is a good thing. And so you can also see that there is we can even zoom in to one of these things and see even more what are the dependencies of the operators from one to another. So that is something that is worth checking out if you are profiling TensorFlow. Intel MKL DNN itself has a profiling mode, which can be easily turned on by setting these 2 environment variables. So when you set these to 1, they basically will dump a CSV output, like comma separate value output to your screen, to std out, to basically characterizing the size of your convolution, what are the parameters of your convolution, what's the time taken, what is all the channels, input width, input height, and all those parameters to a convolution. And similarly, if you have any matrix multiplications, it will also dump the size of the matrix multiplications and the time taken in executing those. And we also internally if you really want to do a deep dive analysis of what exactly is going on, then you can also use Intel VTune Analyzer, which is standard profiling tools that Intel provides, that has been used in HPC application profiling for some time now. So I just wanted to highlight some potential issues that people may encounter when you are using Intel TensorFlow. Some based on our interactions with several customers, and that we have observed that threading is something that is a pain point, wherein if you don't set the right threading parameter, it can lead to oversubscription and can give you very poor performance. So that's why we have, as I mentioned in the previous slide, you really want to make sure you set the inter-op, intra-op, OMP num threads, and the KMP affinity values to the right values for those variables to prevent the situation. So if you don't do it, you typically get an error similar to the box I have on the right, which basically is saying where every thread is spawning. Basically, if you have like a 68 core machine, and you basically will be spawning 68 times 68 threads, which is like too much for the OMP runtime to allocate, and it will just bail out saying, hey, I cannot support these many threads on this system. So that's one thing that you can potentially watch out. That something, if you see this error, then just make sure your environment is set properly. And then there is as I was mentioning in the graph optimization path, so we do convert this TensorFlow layout to MKL layout, block layout, and you don't want too many of these ops in your network. And so if you see too many of MKL reorder ops, that is a sign that you are seeing something. You will see poor performance. So you can observe this in the MKL verbose output. For example, the verbose output dumps when is a reorder done, when is a convolution done, when is a matrix multiplication done. And the next thing is we also have we prefer convolutions with the number of output channels to be a multiple of 16, because the reason for 16 is we basically can fit 16 FP32 elements in a AVX 512 register, and that's the reason why we block on 16. So we are constantly trying to improve performance for non-multiples of 16, but that's if you can control this parameter in your network topology, we prefer that you use convolutions with output channels as 16, multiples of 16. And the other thing is in the timeline view, you want to see mostly MKL operators. If you are seeing non-MKL operators in your timeline, then that is something that needs to be optimized specifically for that, because you are not using MKL for them and you are relying on the Eigen framework to accelerate that, which for which the performance can be suboptimal for Intel. And then finally, we have observed that the same thing that applies for HPC domains, which is the IO pipeline, could be a significant bottleneck, wherein because typically deep learning applications have a large data set for which they want to train on iteratively. So you typically have your typical IO bottleneck either in Lustre file system or some other file system you have on site. So you may want to make sure that you are using the right API, TensorFlow APIs, to do the prefetching of the batch of images to amortize the IO cost. At this point, I will give it over to Vikram, who will go over the scaling results and case study.
Hi, thanks, Vamsi. I guess Roy, you can see me. That seems reasonable. Ray, you can see me?
Yes.
We can see you. Sorry, it takes me a second to unmute.
Okay, sure, no problem. Okay, good morning, everyone. Thanks for attending this talk. So, I've been working with, as part of Intel Parallel Computing Center, I've been working with a few customers such as CERN and Surfsara. CERN, of course, is in Switzerland, and Surfsara is a compute service provider in Netherlands, and also we work with other customers in Gency in France, and so we have some use cases. And I'll go over some of the benchmark, scale out, training, performance, and then use cases. So working with Surfsara, and this data is actually on Intel Xeon Phi cluster on Stampede and Tack. And this is the sort of the popular ResNet 50, and as you can see, we can scale it pretty well with 97% efficiency on Tack on 256 nodes. So that we can scale the now this is using Caffe and not TensorFlow, and I'll come to some TensorFlow as well. This data is slightly older, but as you can see, we can increase the batch size to a significant, much larger, and able to reach convergence to state-of-the-art accuracy in 63 minutes. Next, I'll to go beyond the state-of-the-art accuracy or reduce the time to train, we have actually increased to 512 Xeon Phi cluster also on Tack, and as you can see, we can reduce that to 46 minutes. and then reducing time further, we have scaled it to 768 nodes and reducing that time to 39 minutes. All this data is actually on Caffe framework, and then if you want to, we also saw that if you want to increase beyond the 74% top one accuracy on and this is on ImageNet dataset on ResNet 50, we were able to achieve that on 512 Xeon Phi nodes in 55 minutes. So scaling has been, we are able to scale very performantly, and as you can see some of the performance data here. Some techniques that we have used as and increasing the accuracy further, and what we are calling as collapsed ensembles, and this is very similar to learning rate collapses. And as the chart shows on the left, that we use the Facebook technique of aggressively increasing the learning rate to the first few epochs of the training, and then linearly take it down and decrease that length. But we've seen that that instead of going all the way linearly, if we reduce and then exponentially decrease and then take it back up aggressively and then again reduce, and doing that multiple times actually gets us much better performance. So you can see that the numbers on the plot, it says, the base case being, we can achieving 68% top one, we can actually increase that to like 76.7%. And this is a technique that we've used. It's applicable to other use cases as well, and that's something is published also in a paper on arXiv. And this was all the work was done through Theta. So let me go. So this was all data on Caffe, and then we also looked at, of course, TensorFlow, and I'll show you some of the data on TensorFlow. And this is ResNet 50 benchmark with TensorFlow, and also on Tack. And as you can see that, with this, the time to train here to state-of-the-art accuracy is less than 2 hours with 81% efficiency. The important thing, as you know, in training a model is of course scaling efficiency will get you better performance, but of course the metric is really time to train, and that's what we're trying to get to. And so if we can, with less number of epochs, if we can reduce the time to train, and that's what the customer is interested in. Another use case working with CERN is with CERN uses heavily Monte Carlo simulation for high energy physics particles, and they have a tool called JAN4 that actually does the Monte Carlo simulation. As you know, since you excuse me, since you've done a lot of HPC work, Monte Carlo simulation is extremely compute intensive, and one of the approaches that we are looking at is how can deep learning specifically can help reducing that pressure of compute, and of course, having said that, also meet at the same time the accuracy that the simulations will give you, and then compare that to real data as well. So we worked with CERN and SurfSara to develop the 3D generative adversarial network architecture. And this is people have been looking at two-dimensional, and here, as you know, that the particles through the media and their trajectories require 3D trajectories through, and so we actually use the simulated data and then run it through 3D GANs, and based on the 3D GANs, convolution, deconvolution to describe that whole volume and what the trajectory of those particles would be. So we recently published this data at ISC 18 workshop, and the data here shows, we've taken this and this, of course, work was also done on Tack with 93% scaling efficiency and reducing the time per epoch to about 149 seconds. And you can see that the scaling is 93%. It's not surprising because the model is really small and the communication costs are low, so it scales extremely well. So this was a use case, and we're still further working on this and trying to improve the performance of single node and, of course, on a cluster. Of course, this data is not on Xeon Phi, but it's actually on Xeon Skylake architecture. Another use case that we looked with working with Dell EMC and Theta was on AI, what we're calling an AI radiologist on chest X-ray images. Now, chest X-ray images is the reason. One of the reasons is this is also.
Excuse me for a second. We have a question.
Go ahead.
How is Xeon Phi compared to Core i7 and AMD Ryzen 7 in terms? Is Xeon Phi the best chip for HPC computing?
Yes. Yeah, I think that's, yes, definitely the case. Yeah. Going back to this use case, a few months ago, or maybe early January, Andrew Ning from Baidu and Stanford folks published work on looking at chest X-ray images to identify emphysema and pneumonia. How can they in medical imaging? And this was using a DenseNet 121 network, and so we actually took up that and they showed that they could get good accuracy, and we took up that. Of course, the work was done on GPUs at that time. We took up that and we worked with Dell EMC and Theta to see what we can do and how would other networks, not necessarily DenseNet, but something as VGG16 or ResNet50, trained on ImageNet. So it's a sort of a transfer learning, transfer learning. So that is, you train these networks on ImageNet, but use that model to jumpstart for the chest X-ray images. And we were able to scale this on 200 nodes. And as you can see, going from less number of 64 nodes to 128 nodes to 200 nodes, we can get a significant boost in performance. And we are able to scale it. Now, this data was collected on a Dell EMC cluster, internal cluster, Zenith, that's at Dell. So these are some of the use cases. So I think Vamsi and I are going to give an overview of what we have, what Xeon Phi brings in, what Xeon Skylake brings in, some of the optimizations in TensorFlow, how we can install. There are a number of links in the presentation that you can get to for best known methods. There are blogs that are available. The website has the TensorFlow recommendations, and I think I'll give it to Vamsi, and then I'll have questions from the audience.
Yeah, I think this is my last slide here. So as Vikram was mentioning, I hope the presentation gave a kind of a high-level overview of the work that Intel engineering teams have done to optimize TensorFlow. And we also have heard that good experiences from the NERSC and the LBNL researchers in using Intel TensorFlow on their Cori system, which is basically a KNL for computer. So, and we hope that some of the Argonne researchers will also try this out and do some work on the same kernel machines. That's all I have.
So if there are any questions, We can definitely there's time. So
now that you're out of presentation mode, there are a few questions on the chat. If you switch to that,
So, Ray,
okay.
can I before going into the questions, can I just add something?
Please.
Yeah. So for the attendees, we have TensorFlow installed on Theta, and we've actually been presented on TensorFlow at our various workshops. TensorFlow has, with Horovod, has scaled out to thousands of nodes on Theta. So if you have questions on using TensorFlow and some optimized parameters, please do let us know.
okay.
Right. The presentations from the workshops that were held in February and May are available online, and I can send you links to them.
I think there are some questions here.
Yeah, so going back to the question about relative performance, so I think the person asking the question was wanting to get the relative performance between Phi and Core i7 and the AMD Ryzen 7. So it sounded like you concurred that Xeon Phi was the best for HPC, but how do the three fit together?
So I think so the Core i7 is not is actually a desktop chip. I think maybe the question was actually meant to ask Xeon Phi versus Xeon, I'm assuming, and compared to Ryzen. So as you know, right, Xeon Phi is the only chip among these three that has the high bandwidth MCD RAM, and HPC applications do require high bandwidth because not all of them are compute bound. Several of the fast computations require higher bandwidth. So those can definitely benefit from Xeon Phi, but at the same time, as Intel's next generation of Intel Skylake is also a very good HPC product. So that's also something which has 56 cores. So that also delivers significant amount of flops. And when you put it in a multi-node configuration, it can also deliver significant amount of performance. Comparing to AMD, I mean, AMD has it depends on what kind of benchmarks you're running. It's all, again, I don't want to make a generalized statement. You may want to compare what exact workload you have to what you can get with Xeon Phi or Xeon. And one more thing is Intel has invested significant amount of resources in optimizing the software stack. As you can see from the presentation, it is very important to tune the software stack to get the optimized performance. And Intel has the optimized compilers and runtime libraries like MKL and all these profiling tools that kind of gives you a better experience out of the box for our users and especially for scientists, so that they can focus time on their application domains and not exactly on like tuning low-level kernels such as convolutions or matrix multiplication.
Maybe take the next question.
Yeah, so the next question is, are there some qualitative results to the use case at CERN? I'm interested as GANs are not that stable, and impressive that 3D GANs were used for fluid simulation. This is not related to the webinar, just a curiosity.
Yeah, that's a good question actually. So it's come up in conversations with Lawrence Berkeley Lab as well at NERSC, and we do understand that the GANs are unstable. However, our work actually, we were when we started working on this, we found that at least for this use case, for high energy physics particles, for those showers, it was fairly stable, and it gave us good, extremely good accuracy as well, and very close to what Monte Carlo would give. And we are in the process of actually a camera ready copy of a reviewed paper that we can share probably by next week. But yeah, you're right. I mean, we've also known that GANs are not stable. So, but But at least for us, it hasn't been the case. It seemed fairly stable for us so far. Let's see if there's
Okay. And the last question in the chat is, will the data pipeline I made for TensorFlow GPU with tf.data API, consisting of caching and prefetching, will that work with Intel TensorFlow?
Yeah, so let's see. If you're using, so there are a few ways to use that dataset APIs. So the one is the dataset APIs, the other one is the record input. I think we have used both in our cases, and of course, as the question indicates, it needs to be prefetched. Data needs to be prefetched, and we have had no issues with. We actually, as long, we were able to work very efficiently with dataset APIs or the record input APIs. Any other questions?
Do you have any recommendations for users on inter versus intra versus OMP num threads on Xeon Phis?
Yes. We typically observe that interop should be set to either 1 or 2, or like some value that is less than, like definitely less than 5 or something like that. And the key logic behind is, like, you don't want to, the product of interop and the intraop should not be greater than number of physical or logical cores in the system, because if you have the product of those two increases, then you are oversubscribing. So that's one recommendation that we have. The recommendation is to set the same value to intra and OpenMP num threads. So these are, I put some of these general suggestions in the slide. So let's say if you are using on a KNL on a 64 core KNL, right? Then it is a good starting point to try out is set interop to 1, intraop to 68, OMP num threads to 68. You can increase the OMP num threads and intraop to 136 as well, because sometimes a single thread cannot fully keep the FMA units busy. So you can typically, let's say you can have more than 2 threads, or let's say 4 threads also. So, but we typically don't recommend tinkering with interop that much. As in, we don't want that to be higher number.
Yeah, just to add to that, in certain cases, we have actually increased that interop to larger than 2 because of the fact that, for example, we have worked with a use case with Novartis where the topology is actually, there are not just one pipeline of the network, but actually 7 pipelines going across from and subsampled from at different resolutions, from high resolution to low resolution. In that case, we've actually used interop setting to larger than 2, maybe to 4. The other recommendation would be is having large number of cores and threads. Do exploit the fact that you can actually run multiple instances of TensorFlow on Xeon Phi or Xeon. And when you affinitize those instances to cores, then you need to make sure that, let's say if you're running 4 instances on Xeon Phi on a 68 core Xeon Phi, then what we do is assign 16 cores to each of the instance, and that's so there are 4 instances that gets you like 64 cores, and then maybe leave the other 4 cores to do I/O. However, given the fact that on Xeon Phi there is only 16 gigabytes of HBM, then if your working set is much larger than that, then flat mode may not work, but cache mode would work. So you need to take care of some of these recommendations, and and on the Xeon side, if you're running it on Xeon side, we have been working with images which are much larger than ImageNet, which is like we work with images like 1024 by 1280. So these are much larger images. So because they're much larger images, the memory requirement actually increases significantly, and we've been, on Xeon systems, we have actually consumed up to like 80 gigabytes per for doing some of the classification on training. Okay, Roy. So seems like you're almost at 10 o'clock and almost past 10 o'clock.
We have one more question if
Okay,
you have
sure.
a moment. It refers to your slide where you mentioned poor performance if there are a lot of MKL reorder ops. Do you have any suggestions for what to do to improve that?
I think the reorder ops happen when a certain primitive that you are using in your topology is not yet available in MKL. So those are things that we want to know. So we want to know what is the use case in those, and then so you can put them up on the MKL DNN GitHub page. For example, you can just post your MKL DNN verbose log and kind of give a or kind of mention what is it exactly that you are doing in the network, and because these are things that a user can't do much. We want to just collect these information and add these primitives in future MKL releases.